All right, in this final section, we're going to look at mixture problems. These are basically you're going to have a tank of some sort. It'll usually have a liquid in it, maybe water, maybe a salt mixture, something of that nature. And what you'll have is you'll have a pipe that flows in, and you'll have a pipe that flows out. So usually, the tank itself has some sort of a liquid in it, let's say. Maybe water, maybe salt water, whatever. What's coming in may be anything. It's going to come in here, and inside the tank it's going to get mixed around really well, and then it's going to be shot out the other side. The inflow and the outflow does not have to be the same. It just depends on what kind of a solution you want to achieve in the tank itself. So let's start with an example to show how this stuff works. So for my first example, let's say we have a tank has pure water, flowing into it. And we'll say it's at 10 liters per minute. The well-mixed tank water flows out also at 10 liters per minute. Salt is added to the tank at 0.1 kilograms per minute. Initially, the tank contains 10 kilograms of salt and 100 liters of water. All right, so in this situation here, I'll use the picture I just drew to illustrate. We have water coming in, just pure water coming in, and so that will be at 10 liters per minute. But there's no salt in the water that's coming in, so 0% salt. We also have salt being poured in at a rate, I don't know what structure I want to make it look like this, but let's make a little like tube of the stuff. And out comes the salt into the tank. It's being sprinkled into the tank somehow. And so that's being added to the water. It's being stirred up and then shot out the other side. Also at 10 liters per minute. But this time, I don't know what the mixture is. All I know is whatever we have in the tank is coming out here. So I know it initially starts with 10 kilograms of salt and 100 liters of water. But realistically, we don't know at any given time how much concentration of salt is in there. So here's what we want to do. We want to determine a formula for the amount of salt in the tank at any time t. So what I'm going to do is we'll let A of t will equal the amount of salt in the tank. Now, the way we structure these is it's impossible for me to come up with a formula for how much is in there just by trying to work out, oh, after 1 minute, there's so much salt in the tank. The problem is we're sending stuff out also. So what we look at is the change of the amount of salt that is in the tank. And we have a simple way of looking at it. We look at the rate of salt coming in, so we call it the rate in, minus the rate out. And that'll be the net rate that will constitute the dA over dt. So let's take a look at what's coming in. We know that we have pure water. Pure water has 0 kilograms of salt per liter. However, we are pumping in 10 liters per minute. Well, this is still 0, but we're also adding a component of salt. Salt is being added at 0.1 kilograms per minute. And then finally, out of this thing, we have 10 liters per minute. That's how fast it's going out. However, the mixture in there is made up of salt. And we know that at any time, A represents the amount of salt in the tank at any time. We'll say it that, at any time t. So with that in mind, then, what I need then is the concentration of salt in the tank. So I know I have A kilograms of salt, but I don't know it, but I do know in the tank itself it holds 100 liters of fluid. So there's that part of it. Let me simplify a little bit here. This first part is 0. So I have dA over dt equals 0.1 minus, let me multiply this stuff together. I'm going to get 10 divided by 100 will give me 0.1 also, so I have 0.1 A. Notice that the units of all of these things, I can cancel the liters, and I get kilograms per minute. That's telling us how much salt is accumulating in the tank per minute. Here is 1 kilogram. This was already the right units. And then over here, you can see the same thing. The liters cancel out, and I'm left with kilograms per minute of salt. That's how much is exiting the tank. Well, what you get here is a fairly simple differential equation. You can separate these, but I'll instead use an integrating factor and rewrite it like so. So my integrating factor that I want to use is going to be e integral 0.1 dt, and that'll be e to the 0.1 t. So I'll multiply everything by that. All right, and of course, as always, the left side becomes d of e to the 0.1 t times a, and the right side becomes 0.1 e to the 0.1 t dt, and we're ready to integrate. The left side simple, we get e to the 0.1 t a equals. The right side actually turns out to be super simple as well. When I integrate e to the 0.1 of t, I'm going to get e to the 0.1 of t divided by 0.1. So the 0.1s will cancel, and I'll simply get e to the 0.1 t plus a constant. And then to get a formula for a, I'll do a of t. I'll divide by e to the 0.1 t, and I'll get 1 plus c e to the negative 0.1 t. And now to get the constant, we know that the initial value we had when time was 0, a of 0 was equal to 10 kilograms of salt. So let me throw that in. So a of 0 equals 1 plus c times e to the 0. And a of 0 was 10 equals 1 plus c. And so this gives me c equals 9. So my formula then is a of t equals 1 plus 9 e to the negative 0.1 t. What's going to happen then as time goes on? Well, you can see what this piece right here, as we know, is called a transient term. As t goes to infinity, a of t goes to 1. That means the amount of salt in the tank itself will settle at about 1 kilogram as time goes on. That's because we have fresh water going in, so it's losing its salt concentrate, because then down below we're firing out salt water. Now let's think about this. At some point in time, I'll never actually get there, but when a of t equals 1 exactly, when that actually happens, think about what's going in. You have 10 liters per minute going in, but that's 0 kilograms per liter. You've got fresh water going in, but then the outflow, well, what do you have in the outflow? Inside the tank, there's always 100 liters. Okay, now I'm saying that a of t equals 1, so in the tank itself, let me draw a tank. I have 1 kilogram of salt, but I have 100 liters of water. Now coming out this side then is 10 liters per minute. So if you look at what's happening here then, if I look at the salt that's going out, I have 1 kg per 100 liters times 10 liters per minute. The liters cancel out, and you're left with this here equals 0.1 kg per minute. Now, if you remember, there was a salt shaker that was salting this thing at a rate of 0.1 kilograms per minute. So you can see this is where it reaches a state of equilibrium. Whatever gets put in here salt-wise is getting shot out the other side, so it's keeping that 1 kilogram of salt in the bottom of it. Well, it just mixed in it. I don't want to say the bottom because it's supposed to be well mixed, but it's keeping that 1 kilogram per 100 liters in place while this process goes on forever. A question that might come up: how much water or how much salt is in the tank after 30 minutes? And for that, let's go back to the formula itself. A of t equals 1 plus 9e to the negative 0.1 t. I'll replace t with a 30, and we get 1 plus 9 e. If I put 30 up there, then I'm going to have e to the negative 3. which is approximately 1.448 kg. For example 2, we have a more complicated situation. So a 1,000 gallon tank initially contains 800 gallons of water with 2 ounces of pollution. Well, let me add one thing to that. I don't want to just say pollution, because it makes it seem like there's 2 ounces of pollution laying on the floor of the tank. Let's say it's 2 ounces of pollution dissolved in it. So polluted water flows in at a rate of 3 gallons per hour and contains 5 ounces per gallon of pollution. The tank mixes the water and the pollution, and the well mixed solution exits the tank at 3 gallons per hour. Determine a formula for the amount of pollution in the tank at any time t. So we're going to do the same thing before. I like to draw the pictures of these. I think it's interesting, or it makes it easy to draw or write the equation. So we have a 1,000-gallon tank initially contains 800 gallons of water. So let's go ahead and put that stuff in there. I have my tank. We have initially 2 ounces of pollution, 2 ounces, but we have 800 gallons of water. This is our initial starting position. Now, into this flows polluted water. It goes in at 3 gallons per hour. And it has a concentration of 5 ounces per gallon. Now out the other end, this solution just, whatever solution it is, just exits it. And I know that it exits at 3 gallons per hour. So the same is going in is going out. So it's always going to be over 800 gallons, or that's how many gallons will always be in the tank. So as before, A of T will equal the amount of pollution at time T. Now remember, we're talking about pollution. That's the thing that's being measured here. Pollution is measured in ounces, and we are going to work the differential equation that talks about how much the amount of pollution is changing in the tank at any time. So if I look at dA over dt, once again, that's going to be the rate in minus the rate out. Now let's go ahead and put those in. Coming in, I've got 3 gallons per hour times 5 ounces per gallon. You'll notice the gallons cancel out, and you're getting your ounces per hour, which tells us that's how many ounces of pollution is flowing per hour into the tank. Now leaving the tank, rate out, I know it's 3 gallons per hour, but now, since this is changing in here, 2 ounces is just the initial amount. So since I'm saying A of T is the amount of pollution in the tank at time T, that means I'm going to have A divided by, and we always have 800 gallons of water. And that there is ounces per gallon. I urge you to use the units as well, so that you know you can do some canceling and know that you're dealing with the right things. For instance, here I'm going to get 15 ounces per hour minus, once again, the gallons will cancel over here, and I'll have 3A over 800 ounces per hour. So these match up. So the differential equation that I want to solve is dA over dt equals 15 minus 3A over 800. And I'll do just like I did before. Like I said, you can separate if you want. I'm going to use the linear equation and do integrating factors. So I'll have dA over dt plus 3 over 800 A equals 15. So my integrating factor will be e to the integral of 3 over 800 dt, or e to the 3t divided by 800. I'll multiply everything by that. Of course, you've seen this before. I'll even just go straight to the integral. D of e to the 3t over 800 a. That's the integral of 15e to the 3t over 800 dt. Of course, the left side is easy. E to the 3t divided by 800a equals, in the right side, I'll have to divide by 3 over 800 or multiply by 800 over 3. So I'll get 15 times 800 over 3 e to the 3t divided by 800 plus a constant. And I can do a little simplifying, like 3 goes into 15 5 times. And then I'm going to divide through by the e to the 3t over 800. And finally I arrive at the formula, A of t equals 4,000 plus c e to the negative 3t divided by 800. And then the initial amount, I was told that A of 0 was equal to 2. So that tells me that 2 equals 4,000 plus c, because this piece will be 1. So then c equals negative 3998. So my formula then A of t will equal 4,000 minus 3998 e to the negative 3t divided by 800. As t goes to infinity, a of t goes to 4,000. So the most that that tank can handle is 4,000, and this will go up if you actually drew it. 4,000 would be a horizontal asymptote, and the graph would curve up to that asymptote, not touch it, but it would curve up to it and tend to it. Another question: when will the tank contain 500 ounces of pollution? I know that it eventually will, because if it will eventually contain 4,000, if you just let this process go, it'll go to 4,000. That means it's easily going to hit 500 ounces at some point. So let's solve that equation. 500 equals 4,000 minus 3998 e to the negative 3t divided by 800. Subtract the 4,000 and divide by the negative 3998. I'll get 3,500 divided by 3998 equals e to the negative 3t divided by 800. Natural log, multiply through by negative 800 over 3, and we have negative 800 over 3 ln 3,500 divided by 3998 will equal t. T will turn out to be approximately 35.475 minutes. So there's the answer to that part. Now, one last question I have. Suppose that when there are 500 ounces of pollution in the tank, the inflow of pollution is cut off and fresh water is pumped into the tank. At 2 gallons per hour, and the outflow is increased to 4 gallons per hour. This is a means of cleaning out the tank, I'm assuming. So now, determine a formula. For the amount of pollution in the tank at any time t. I need to remind myself of something, and possibly you didn't see it as well. When I go back to this problem, I made a mistake. Back. Right here. Pollution is coming in ounces per hour. What did I do? When I answered, I put it in minutes, and that's not true. The time was measured in hours. So let's go ahead and take this out and change this to hours. Okay, so everything will be in terms of hours from now on. All right, so once again, let's draw a picture. Now we have reached 500 ounces of pollution, 500 ounces. This is the initial amount, and we had 800 gallons of water. So at this point, we have water is being pushed in at 2 gallons per hour. And that's 0 ounces per gallon. But leaving out, we are leaving here at 4 gallons per hour. But how much pollution is there in that thing? Remember, you're losing so much water or tank fluid because essentially you are losing 2 gallons of hour. So minus 2 gallons per hour of tank mixture. That's the rate how fast things how fast the volume of the liquid in the tank is changing. So let's go ahead and take a look at our differential equations. I'm going to do the same thing I did before. dA over dt. And we'll do the same thing. 2 gallons per hour times 0 ounces per gallon. I know it's silly to do this piece. But minus, now we're doing 4 gallons per hour times, now what's going on here? We don't always have 800 gallons in here. We have 800 minus 2 t, if t occurs after the time that we said it was. And then how much is actually, how many ounces? Well, we're calling that A. And that would be ounces per gallon. Now, I want to be a little careful with this piece here because that's not quite it. This makes it look like T starts when you get, it looks like T starts at 0, and that's not true. Our initial value is this. I dot V is that A of 35.475 equals 500. That's not A of 0, that's A of 35.475. So I need to fix it up in here. And here's, let me change this then. We have A, there's still A, is what's that's going to be called, but minus, remember, we are losing, a net of 2 gallons per hour is leaving the tank. So what I'm going to have here, though, for that piece, do you see what I did here? Now, when T equals 40 equals this 35.475, this piece will zero out, and I'll have A over 800 like we should have. And then when T is faster than that, the amount of pollution, this thing here will start to become bigger and bigger as T is larger than that number. Now, if we insist that T be greater than, for this process, T has to be greater than this because that's when 500 ounces have accumulated in there. So this is actually the correct amount. If T were measured at the beginning, that's a different story, but T will only start at 35.475. So when T equals that number, this piece zeroes out. I have A over 800 like before. So dA over dt, the first part is 0. The second part, then I'll get negative 4. That's this piece right here. And then this is the right, this quantity here is not actually the one you want. You want this quantity here. So I get 4A divided by 800 minus 2 times T minus 35.475. Now, I can take out a negative 2 from the denominator and rewrite that as, so the numerator will be negative 4A. The denominator will be negative 2 times T minus 35.475 minus 400. And then I'll take out the negative 2 with the negative 4, and I'll be left with 2a divided by, now inside of here, when we simplify, I'll have t minus 35.475 minus 400. Or my final version of the differential equation will look like this. 2a divided by t minus 435.475. And that's what you're going to have then. So then to solve this one, I think I'm going to separate terms. It seems a little bit easier here. I'll have dA divided by a equals 2 over t minus 435.475 dt. Integrate. We'll have the natural log. Now the amount's never going to be negative or 0, so we'll put ln of a. I don't need absolute values. 2, and since t is greater than or equal to this number here, well, t was greater than or equal to that number actually, I'll put ln, I guess I can throw the absolute value in there, t minus 435.475 plus a constant. And at this point, let me find out what the c is before I do anything else. So I am going to start, t was 35.475. Let's go ahead and throw it in there. So I knew that a of 35.475 was equal to 500. This will allow me to find the c. So I'll have ln 500 equals 2 ln. If I replace t with the 35.475, I'll get negative 400 plus a constant. And of course, I'll squash that thing. I'll have ln of 500 equals ln of 400 squared plus a constant. That'll be ln of 16, 1, 2, 3, 4, 4 zeros, 160,000 plus c, ln 500. I'll subtract ln 160,000 both sides, and I'll end up with ln of 500 divided by 160,000 equals c. I'll take out 2 zeros, and I'll have 5 over 1,600, and I know that can be simplified even more. Let's see what we have there. Let's see, 5 goes into 120 times. 16 times 20 is 320. So I have ln (1 over 320) equals c. Now let me go back to the equation that I was setting up, and here it is over here. So I'll have ln of a equals 2 ln t minus 435.475 plus c. I'm going to leave that there for just a minute. Now I'm going to square this part over here, which means I'll be able to drop the absolute value. So I'll get ln of a equals ln of t minus 435.475 squared plus c. And then I'll take e to both sides, and I'll get a of t equals t minus 435.475 squared times e to the c. So I didn't actually want c. I prefer to have e to the c, which is just 1 over 320. So a of t equals 1 over 320 times t minus 435.475 squared. And remember, t has to be greater than or equal to 35.475 for this to work, because we're talking about when the pollution got to 500 ounces was at that time.